Hey, thanks for coming back. Now let's take a look at the table we were looking at last time. And if you recall, we had two treatments, a standard treatment and a new treatment. And the outcome measurement of interest was a dichotomous outcome. Did the patient improve, yes or no? Now based on a dichotomous outcome, your summary sample statistic for the two groups would be the percentage of patients who improved. And remember again, these two samples are presumed to be representative of some much larger target population out there. And we're trying to estimate what percent improvement is there in the target population. And these are our samples. We also mentioned last time that if you know a percentage, you do not know how precisely you have measured that percentage estimate without also indicating what the sample size is. So in this example, we had 100, sample size of 100 in each group. And then we performed a statistical test, a formal hypothesis test, shall we say. And the hypothesis test is there a difference between the two treatments, a difference in the target population? So our estimate was there was a 16% difference. Now between the percentage and the sample size, we can estimate what's called the standard error of the sample statistic. And this is the thing that tells us how precisely we are measuring what we're trying to measure. So here we have the standard errors written in for the individual groups and then for the difference between the two, which gives us a measure of how precisely we've estimated the parameters. Now you notice in this particular example, we got a p-value of 0.15. Now as you remember, the p-value gives you a continuum, a measurement of how much information we have against the null hypothesis. The p-value is small, it tells us that the null hypothesis is not likely to be correct. Now what is missing from all this now? So we know the null hypothesis is not likely to be correct, but what do you really want to know? You want to know how much of a difference is there between the two treatments in the target population. So what we really need to add into this table is a measure of that difference, and that measure is called the confidence interval. Okay, look at the additional information we now have. We not only know the estimates for the standard treatment, the new treatment, and the difference, we also have an estimate of where the true value lies in the target population. And that's what this is, an estimate of a 95% confidence interval. That means we're 95% confident that the true answer lies somewhere within this interval. And this concept of the confidence interval is much more important in terms of what you've really learned than just simply looking at the p-value. In particular, let's go over to the results of our hypothesis test. The p-value was 0.015. That's very exciting. It's a very small p-value. But look at the confidence interval. 3.2% to 28.8%. That means the real difference between the new treatment and the standard treatment in the target population, it might be very large. It might be 28.8%. It also could be very small, 3.2%. So this sort of tempers a little bit the enthusiasm about having a small p-value. And it tells us we have to be a little bit careful before we run around jumping up and down saying how great the new treatment is, because it might just be a little bit better than the standard treatment. Now let's look at the case where we have a sample size of 50 instead of 100 that we had before. Okay, so here's our results for the sample size of 50. And let's go right over here to the difference between the two treatment groups. And in this case, recall the difference was still 16%. We presumed we had the same results from a percentage point of view. However, the sample size is now 50 in each group. The p-value, as you recall, was only 0.086. So those of you who believe in strict hypothesis tests would say, oh, there's no statistically significant difference between the two groups, okay? Which in the old days was falsely interpreted as, oh, the two groups have the same percentage. That's not at all what the p-value here is telling you. And this is given to you nicely by looking at the confidence interval of the difference. Now, the upper value of 34.2% means, even though it's not statistically significant from your point of view, it still could be true that the difference for the new treatment versus the standard treatment is greater in the new treatment by as much as 34.2% more. However, look at the confidence interval. What does this confidence interval tell you? The new treatment might be better than the old treatment by 34.2 percentage points in terms of the percent who improve. However, the negative sign here tells us that the standard treatment might be, in fact, better than the new treatment, but only by 2.2%. But look at this conclusion. What conclusion do you draw from this confidence interval? Between the two treatments, the results are either equivalent or the new treatment is better. So between the two treatments, if I'm the patient, I certainly prefer to have the new treatment. Okay, so we know the confidence interval contains the real information, at least in my mind. So here's a little assignment for you. Take a paper you're reading and find yourself a p-value, and where the authors don't give you the confidence interval, and then construct your own approximate 95% confidence interval in the following way. You take the estimate plus or minus 2 standard errors. Now, the 2 is not exactly the right factor to put in there, but we're talking about concepts in this. We're not talking about getting everything precisely right and exact, okay? So look at that confidence interval, and then see if that tells you anything different than you thought you would have by just looking at the p-value.